in the last couple of lectures. And also some other things that we won't get to yet, like induction. So we'll have just a whole set of different stations you can move around to. And so it'll be kind of fun, kind of like that electrostatics one that we did before. That was really fun, where we just mess around and play with the equipment and try to figure out what's going on. But
The exam is a week from next Tuesday. It's like a week and a half.
Tuesday.
Right.
Tuesday before next.
Perfect.
Any other questions? Okay, so let's just review where we left off last time. We had two different force relationships. One was for a single charged particle moving in a magnetic field. And so we looked at a few of those, and we'll look at more of those today. But the other one was IL cross B. And so this was for the force on a current carrying wire. And this, of course, assumes that the wire is straight. If the wire is bent, then we have a calculus problem, which we'll look at a little later on. But let's just make sure we can do the long straight one first. And so remember that the direction of L here is in the direction of positive conventional current. So if we want to do and let's say for this example that theta is equal to 30 degrees. That looks like a little more than 30, but let's just make it 30 so that the numbers are easier to calculate and I don't have to pull my calculator out. So for this problem, we could set L equal to 2 meters. Let's set our magnetic field equal to 10 to the minus 2 Tesla. Theta equals 30 degrees, and we'll have a current going through here of 10 amperes. Okay, and so first of all, what would be the direction of the force? If you forget everything else I said, which directions could it be? Either out or into the board, right? Because it's got to be perpendicular to the plane that's defined by V and our vector L, okay, which is in the same direction as the current. So it's got to be either in or out, and so let's do what we did before. We stick our arm in the direction of the current like this, and we curl our fingers in the direction of the magnetic field. So can everybody do that? Do you understand what it is that I'm doing there? I'm taking my arm, I'm pointing it in my right arm, pointing it in the direction, and then I'm making the tails of the IL vector and the B vector come together at the base of my hand. I'm curling my finger toward the head of the B vector, and so that gives me a force that's out of the board and is uniformly distributed along the entire length of the wire. Okay, and so that force then, for this example, would be equal to the magnitude. We don't care about the direction anymore. We got the direction. It's out of the board. But the magnitude is going to be I, so that's 10 amperes, times L, 2 meters, times B, 10 to the minus 2 Tesla, which is actually a fairly big magnetic field. This is 100 times bigger than the Earth's magnetic field, times the sine of 30 degrees. Okay, so the sine of 30 is 1/2, and so that cancels out the 2. So I get 10 times 10 to the minus 2 is 0.1 newtons. Okay, so we have 0.1 newtons uniformly distributed along the entire length of that wire and pushing it out toward us. Are there any questions about that? This is our basic operation. Everything else builds from that. So if we were to, let's say, have a wire that goes through a magnetic field. And that magnetic field might be, say, produced by a magnet. We'll be doing this in lab today, by the way. We'll be deflecting wires with a magnet. What we would see then is that with no current flowing, of course, the force on that current carrying wire is 0. But if we have the current going up like this, then we do IL, can we all do this? IL cross B, that would give us a force that points to the left. Sure you can do this. For this one, with the current going down, we would go IL cross B, and this would be a force going to the right. You should be able to do that one too. And so sometimes you've got to change the orientation of your hand. Sometimes it's easy, like here, IL cross B. Here, you've got to kind of turn it around and twist it, and just be careful if you've got a bad shoulder. Dislocate your shoulder. Okay, but those would be the directions of the forces. Now, if the wire is strong enough to handle that force, then the wire won't deform. But if the wire is free to deform, it will push out either to the left or to the right, like that. We already looked at this example last time. That was the rail gun. And that similar kind of technology is used in some of the amusement park rides, like Superman at Magic Mountain. It's accelerated. It's kind of a rail gun type of thing. It's accelerated along with a magnetic field, and then you kind of go up, and then you see Superman up there, and then you come back down. You can get going like 100 miles an hour just in that short distance, and so that rail gun thing is pretty cool. What about if the wire segment, though, is curved? Well, then we got a different problem. And I'm going to redraw this, so I'm going to for a second. For our curved wire segment, let's say that the radius of the wire is R. The lengths of the wires here are L and L. And the current, let's say, is going through this way. So the current then goes up and around, and down, and along that length there. And let's put this in a magnetic field that's coming out of the board. And a lot of the examples I was using last time, the magnetic field was into the board. And so let's just get used to what happens if it's coming out of the board. We'll assume this is a uniform magnetic field all the way through here. It's coming out of the board right at us. So the magnetic field vector B is pointed this way, and it's uniform. So you can imagine, for example, that behind the wire, you've got the big north pole of a horseshoe magnet, and on the front side, you've got a big south pole of a horseshoe magnet. And then this wire is sitting in between that space. And so what I want to do here then is find the net force on this curved wire segment. Which we can break up into 3 different parts. We'll call this part 1, we'll call this part 2, and this part 3. And by symmetry, I think that we can see that F1 and F3 are going to point in the same direction and have the same magnitude. Because you have the same length of wire being exposed to the same strength of magnetic field all the way through. And so let's just get the basic direction of the force. What's the direction of the force? Okay. IL cross B, like this. Can we all do that? IL, B, up. This is F1. This is F3. So those are easy. F1 equals F3 is equal to ILB. Times the sine of what? What's the angle between L and B? 90 degrees. Remember, that's our vector cross product in terms of its magnitude. In general, I, L cross B has a magnitude. It's equal to the magnitude of I times the magnitude of L times the magnitude of B times the sine of the angle between. Okay, and so we just take the magnitudes of all of those, and then we multiply it by the sine of the angle between them. And that's our definition, if you recall, for a vector cross product. Now, we're simplifying this a little bit, because you could have components of the current, say, in the x and the y direction, and you could have components of the magnetic field in x, y, and z. And if that's the case, then you can't simplify it this much. You have to use what's called a determinant to get it. And so we'll talk more about that later. If you do determinant, you have something like I, J, K hat, and then here you have Lx, Ly, Lz, and then Bx, By, Bz. And you'd take the determinant of that. Don't worry about that yet. We'll get to that. And we'll see that it reduces to this result. That for a simpler problem like this, where we've already got the distances and directions established in terms of just our good old familiar x, y, z coordinate system, where x, y, and z are all the directions of orientations of the vectors, or at least it's just some angle between x and y, for example, then this is plenty good. So what we're interested in then is the net force on this central segment. That's the challenging part. The rest of it is pretty easy now that we've got this all under control. So here's our current I. Here's our magnetic field B. So what we need to do then is say that D force is equal to I dl cross B. Because the L's are pointed in constantly changing directions. And so this little dl is a different dl than this one here. And that's going to be different from this one over here. Not in magnitude, but in direction. The directions of these dl's are constantly changing. So that means, because that dl is what defines the direction of the force, that means the direction of the force is constantly changing on the wire. Okay, and so let's just look at a little tiny dl. And as we did before with electric forces, let's look for symmetries. So here, let's say that this angle is theta above the horizontal. Then I dl cross B is going to point in what direction? Radially outward. Very good. That's exactly right. And so I'm going to give that a length, even though it's an infinitesimal quantity, because we're going to be adding vectors, and so it's nice to have something that has a length to it when we're adding these things together. And so what I'm going to be looking for then, what I'm kind of guessing is happening, is that this df is going to be broken up into horizontal and vertical components. And so I say to myself, well, is there some other symmetry that could cancel out one of the components? And my answer would be, well, what if I went an equal angle theta on the other side? This may remind you of some of the kinds of symmetry things that we did with electric fields before. And these strategies are very similar. So here we do I dl cross B Can you do that one too? IDL cross B, that's going to point radially outward in this direction, DF. Okay, and so if this angle is theta, then that makes that angle there theta. That makes this angle there theta. And so now can you see that if we put these together, this is DF, that the DF cosine theta components will cancel. And what I'll add then is the DF sine theta components. And we're doing this pair by pair. So I'm saying, okay, for this angle, I've got that one. For this angle here, I've got this one, but then I've got this one. So that for every one that has an x component that points off to the right, I've got another one at an equal angle on the other side that has a component that points off to the left. So that the only thing that survives is df sine theta. So this gives us the direction. And that's what? Up. And that should satisfy our intuition as to what's happening here with wires 1 and 3. The net force on them is up. And so here you've actually got a component of current that's going this way and a component of current that's going that way. But the component of current that's going that way is going to cancel out the component of current that's going down that way. So really all you're left with is the component of the current that goes straight across. And so what we could do then is say that our force total is going to be the integral of df sine theta. And so what's theta? No. Well, oh, you said 0 to 180?
Yeah.
Okay, good. I thought you said 180. Is theta the same theta as we have here? IDL B sine theta. Is that the same one? No. Be careful with, especially if you're an equation hunter. I know none of you would do that, but I've noticed before in some of my other classes that some people are just looking for an equation. And they don't care why it works. They just want to get the right answer. But they don't understand. They never took the time to understand what was actually happening. And so they're just grabbing an equation. And, oh, I see theta there, so I'll just plug something in for it. And maybe half the classes I've ever had, I've had huge numbers of students that have done that. So that's something to watch out for here. You really need to take the time to understand what's going on and not just hunt for an equation that you hope is going to work. So here, this theta is going to vary. It's not the same angle as the angle between DL and B. That angle is always 90. This is a different angle. It has a completely different meaning in this problem. I should probably call it phi or something, but I'm calling it theta just to emphasize the fact that it's easy to get confused. And so be careful with that. Okay, so what's my magnitude of df? The magnitude of df is equal to the magnitude of I times the magnitude of dl times b times the sine of theta. Okay, so what's theta? Isn't it 90 degrees? Isn't that what we just did over there? 90? This isn't the theta I'm talking about here. This is 90 degrees. So df is IDLB times 1. So df sine theta is going to be IDL B times the sine of 90 times the sine of theta. Okay, so now what we're doing then is we're integrating DL. Anybody have any suggestions about how to do that? How am I going to write it though? I don't have consistent integration variables. Theta is varying and DL is my integration variable. So how do I make that consistent? Okay, good. And what would I do in polar? What is DL equal to, in other words? DL is your arc length. R d theta, very good. That's the way that we connect this in with a varying angle. R isn't changing, right? So this isn't that hard, but you have to see what's happening. You have to really be able to visualize this situation so you don't get the angles mixed up and that you know how to integrate this thing as a function of a single variable. Okay? And so the next step then is to write this as the integral. And here we could go, say, from theta equals 0 to pi, because that's our integration variable, I b times r d theta, so that's sine theta d theta. Is everybody seeing that that is a logical step from the previous thing? And remember, it's dl sine theta because df sine theta because of the fact that the df's have horizontal components that tend to cancel and vertical components that tend to add. Okay, so all we have left to do then is to integrate, because I, R, and B are constants. We pull them outside of the integral. This is just the integral from 0 to pi of sine theta d theta. Integral of sine is what?
Negative cosine.
Negative cosine. So that's minus IRB times minus cosine of theta evaluated from 0 to pi. So the cosine of pi is -1. So pull this out. I'm pulling the minus cosine out to here. So the cosine, so this is minus IRB times -1 minus 1. Or the minus signs cancel, this gives us -2 IRB times -1 is just 2 IRB. So that's F2. So we can say then that F1 plus F2 plus F3 is going to be ILB plus 2 IRB plus ILB. This is equal to 2IB times L plus R. And so that is our answer then for the total force. And this would be times some unit vector that points in the positive y direction, or what we could call the j hat direction. And notice here that this distance is 2r. And this distance here is 2l. So what this is really equivalent to is just evaluating the force on a straight wire segment that has a length here that's 2r and a length here that's 2l. And the reason why that works is that these horizontal parts of the current are going to add together to produce an upward force, but the vertical components of the currents are going to cancel out. And so that's why it's equivalent to just a long straight wire that has this length in the middle. Any questions about that? All right, next, what I wanted to do is look at the process of what we call velocity selection. And so this is a way in which we can pick out the velocity of an object, of a charged particle, by means of exposing it simultaneously to electric and magnetic fields. So why would we want to do this? Why would we want to select for a certain velocity? Well, because you might want to take that particle, which has a particular velocity, and then make it go around in a circle. And then you'd want to know what the radius of the circle has to do with, say, the mass of the object. So what I'm going to be leading into is the design for a mass spectrometer. This is a way in which you can measure the mass of isotopes by accelerating them to a certain speed, but you have to know what that speed is. Then by measuring the radius of the circular path that they take, you can then get the mass of the isotope from that and figure out what the percentage of the mass is in your sample. That is an isotope. But to do that, let's just look at this process of velocity selection first. So here we've got a particle. Let's say it's positive for the moment. And let's put it in the middle here. So here's our positive charge. And it's moving with a velocity v to the right. And so what's the direction of the electric force going to be on this object? If it's positive. If this is a parallel plate capacitor and semi-infinite in terms of having a constant electric field between the plates. Okay, if it went up, then wouldn't it be attracted toward positive and repelled from negative? So the first thing I look at is not the direction of the electric field, but rather is it going from positive to negative or negative to positive? Then I don't ever make a mistake like that. Okay, and so remember then that a positive charge is going to experience a force that's equal to QE. So this is the electric field. So the force must be in the same direction as the electric field, right? If it's a positive charge. If it's a negative charge, then that's reversed. Okay, so we know that the force on the charge is QE. Or you can cheat and just look at this picture over there. The other thing that we want to try to cancel out here is the magnetic force. So for a certain velocity, we have a velocity-dependent magnetic force. Remember, the electric force is not velocity-dependent. So the way that we're selecting for this velocity is by adjusting the magnetic field in such a way as to get a balance between the vertical forces so that there's no net deflection. Okay, and so if we do this then with a magnetic field that's into the board, QV cross B, okay, should be able to do that. It gives you a force that's up times the sine of what? 90. Because here's V and here's B, they're perpendicular to each other. So don't forget about the fact that there's that sine of theta in there. But if it's 90 degrees, then that term is just equal to 1. Okay, and so for a certain specific value of the velocity, you have an equilibrium. QVV equals QE. Notice here that the charges cancel, so it doesn't matter what the charge is. You're selecting for a velocity, could be doubly ionized, could be triply ionized, could even be a negative charge. If we're a negative charge, then the electric force would be up, and this would be QVB. That would be up for a positive charge, but down for a negative charge. So it could even be negative. And because the charge cancels out of this force expression, this is the sum of the vertical forces is 0. Okay. For no deflection. Then what we got is V is equal to E over B. So we've selected for this velocity. Select from what? Well, you might have a cathode ray tube over here, and you might have something that fires electrons, and then you accelerate it through some electric field like that, and by the time it gets out of that electric field, it's moving at some particular velocity. But not exactly, because there may be some variation in how fast the electron was being ejected from the cathode ray tube, and there might be some variation in the direction too. There are all kinds of reasons why this velocity might not be quite what you would expect it to be. And so you don't want those screwing up your experiment later on. You want to know exactly what the velocity is. So you screen out all those other particles. If the velocity is too high, the velocity is greater than E over B, what is the particle trajectory? It's going to curve up. So this is the trajectory if V is greater than E over B. Because then the magnetic force is going to dominate over the electric force. Whereas, I think you can see that the deflection will be down if V is less than E over B. So only for this undeflected path do we have the velocities equal to E over B. Okay, so let's say that you already have, that you're selecting for velocities be around 10 to the 5 meters per second. And you have an electric field already that's equal to 100 volts per meter. Let's find B. What magnetic field would we need to select for this velocity? Well, then you just say that that magnetic field is equal to E over B. So that would be 100 volts per meter divided by 10 to the 5 meters per second. And so that would be 10 to the minus 3 Tesla. Okay, and so this would still be maybe 10 to 100 times greater than the Earth's magnetic field. So the Earth's magnetic field probably wouldn't have much of an effect on this thing. But if you wanted the magnetic field to be bigger than that, so that you don't have to worry about interference with the Earth's magnetic field, then you could do that by making the electric field 1,000 volts per meter. Then you could select for this velocity and have a value here of 10 to the minus 2 Tesla. And then you'd have very little influence with the Earth's magnetic field. You wouldn't have, in other words, you wouldn't have to worry about how you orient your device in a room, because the Earth's magnetic field wouldn't be competing with it. Okay, so once we've selected, then the next step in the mass spectrometer is to send that particle into a region of uniform magnetic field. So I'm going to need to backtrack for a moment and look at what happens when particles move in a uniform magnetic field. we stated before that the force is equal to Q V cross B. And so if the force then is perpendicular to V and B, but if it's perpendicular to V in particular, that means that what we're dealing with is a centripetal force. Only if the force has a component in the direction of the velocity do we have a change in the speed. So this doesn't produce a change in the speed, and it does no work. Because work is the integral of f dot dx. So in this case, this would be times the cosine of 90, because the direction of motion is perpendicular to the direction of the force. So just like with other centripetal forces that we saw before, like a mass on a string, that does no work. You make that go around and around in a circle, there's zero work done. But the direction is changed. So the V does change. And so we can see then how that's going to work. Let's say that the particle is moving along like this. It's got some velocity v, and then suddenly it enters a region of uniform magnetic field. Or maybe the magnetic field is turned on. Or for some reason, it's here. Let's not worry about how it got here. Let's just say it's there. And it's moving with that velocity. Then we can do QV cross B. That's a force to the south. So that's going to deflect it a little bit. And now it's moving in that direction. QV cross B. That's going to deflect it a little more. And so the direction of the force is always going to be pointed toward the center of spin. By the time that it deflects to here, we do QV cross B, forces toward the center. So this is good for you to practice with. Just show yourself that the direction of the force, no matter where you are on this thing, as the velocity keeps changing, that causes the direction of the force to always act perpendicular to that new velocity, and therefore point toward the center. And so we're dealing then with a centripetal force. So force then is QV cross B. Let's assume that V is perpendicular to B. Now it may not be. And we'll see some examples of this with the Earth's magnetic field, where you actually get a helical path, because there'll be a certain component that'll get no force, and there'll be another component that'll make the thing go in a circle. So that gives rise to what's called synchrotron radiation. But here, in this simplified example, we'll assume that all of the velocity is perpendicular to the magnetic field, and there's no component in this direction to the motion. Then we can see that the force, F equals QVB sine 90, equals the centripetal force, mv squared over r. Okay, and so if you don't remember centripetal force, go back and look at that carefully, because we need that again. So we can then find the radius of the circular path if we want to. The velocities are going to cancel in this expression. So we solve this for r, we get mv over qb. Okay, so for this example then, let's say the q, just to make the numbers easy, is equal to 10 to the minus 10 coulombs. Mass, let's set equal to 10 to the minus 3 kilograms. Velocity equal to 10 to the 6 meters per second. And the magnetic field equals 1 Tesla. Then we could find the radius of that circular path. That would just be equal to m, 10 to the minus 3 kilograms, times v, 10 to the 6 meters per second, divided by 10 to the minus 10 coulombs times 1 Tesla. Okay, and so this would be 10 to the minus 3 plus, no, it's 10 to the 3 plus 10 would be 10 to the 30. This is 16, 13. 10 to the 13 meters. So this would be a very big radius path for the numbers that I've chosen here. Let's try it for a proton experiencing a magnetic field above the Earth's surface that is equal to 10 to the minus 5 Tesla. So the mass of a proton would be 1.67 times 10 to the minus 27 kilograms. The velocity, let's say, is 10 to the 6 meters per second. Okay, and so this could be like a solar wind particle. So you could have a particle being shot out by the sun. The sun evaporates something like 1 million tons of high-energy protons per second. Okay, and so a lot of those come walloping into the Earth, and they're deflected by the Earth's magnetic field, so that we don't get some of the harmful effects from these high-energy particles. Things like evaporate in our atmosphere. Our atmosphere would be gone. If it weren't for these magnetic effects that are going to deflect these protons in a way that makes us safe. Okay, so here we're making V 10 to the 6 meters per second, and then the charge is, of course, the charge on a proton, 1.6 times 10 to the minus 19. So for this problem then, R would be equal to M, 1.67, 10 to the minus 27, times V, 10 to the 6, over Q, 1.6 times 10 to the minus 19, times B, 10 to the minus 5 Pascal. So that gives me 1.28 times 10 to the 3 meters. Or 1.28 kilometers. So that's a reasonable number. Not nearly as big as the size of the Earth. And so what you tend to get then are particles that are evaporated from the sun moving in circular orbits that are on the order of a few kilometers or so. But superimposed on that motion, we also have the motion that is associated with the velocity being parallel to the magnetic field. Okay, and so if the particle is coming in like this, and the magnetic field, let's say, is pointed in this direction, B, then you've got a component of the velocity that's parallel and a component that's perpendicular. And so the part that's perpendicular to the magnetic field is going to cause circular motion. So that's going to look like that. So you got QV cross B, and so that's going to give you a circular motion that looks something like this. Can everybody visualize that? We go QV cross B, and here the velocity is this way, so we go V cross B, and so that's going to create a circular path like this, like the one that we are showing here. But it's going to be parallel to that wall. The plane of that thing is going to be parallel to that wall. Okay, because the velocity is perpendicular to the magnetic field. This part doesn't contribute to the force. There's no force on this part, and so the net effect then is for the circular path to drift with time. Okay, so the V parallel component has no force. And so the result then, when you have velocity components that are perpendicular and parallel to the magnetic field, is helical motion. Helix is like a corkscrew. And so this is the kind of thing then that you expect. If you've got a particle that's moving with some components that are parallel to the direction of B, but some components that are perpendicular to the direction of B, the part that's perpendicular is going to make it go around in a circle, but that circle is going to drift with time. And so that's what you would expect then with the Earth's magnetic field. The Earth's magnetic field, depending on where the particles hit, there's going to be some component of the velocity, v, that's going to be perpendicular. So that'd be this part, v perpendicular. It's going to come in like that, perpendicular to the magnetic field. And then this part here is going to be v parallel. And so the V parallel part is going to make it drift with time. So it'll do this kind of thing, and then the radius will change because the components of V perpendicular and V parallel are going to change as the direction of the magnetic field changes. And when particles accelerate, they produce radiation. This is something that we'll show later when we get to electromagnetic waves. But this is what causes what referred to as the Van Allen radiation belts. And so this then is what we're protected from when we've got high energy charged particles being evaporated from the sun. If we didn't have this magnetic field umbrella, then these high energy particles would just hit the particles in the atmosphere and knock them off. And so we'd be losing a statistically important amount of our atmosphere every year. And over 1 billion years or so, it'd be all gone. And so the Earth is the only planet in the inner solar system that has this kind of magnetic protection. So what does this tend to do? Well, this tends to deflect the particles so that they move along the magnetic field lines, because that's the direction in which there's no force acting. And so these particles then have different components, V perpendicular and V parallel. But the net effect of this is to force the particles to move in spiral paths along the Earth's magnetic field. Now what if the velocity were much bigger then? What if we had a velocity of 10 to the 8? Then that would be like 1/3 the speed of light. It's 3 times 10 to the 8 meters per second is the speed of light. So if they're moving at 1/3 the speed of light, then the radius is going to be 100 times bigger than this. And so 100 times bigger than that, 120 kilometers, 128 kilometers, that's still not comparable to the size of the Earth. But what if they were electrons? Electrons, how would that change the radius? Or make it smaller or bigger? Good, because the radius is proportional to the mass. So R is equal to mv over qv. And so if we go back to our original picture then, here, let's just make this a negative charge, equal charge, so that means equal magnetic force, right? Magnetic force is only QVB, it doesn't have any M in it. So the charge is negative, so that changes the direction of the force. So the force, instead of going up, is going down, but it has less inertia. So it has the same force, but it's easier to turn. And so that's why the radius goes down. M is smaller here, V over QV. This is electron. This is our proton. M, V over QV. We can see that the radius is way bigger, and so it'll go around, in this case, in a smaller circle. Okay, and so you can also get electrons then moving along these paths, as well as protons. They just go in the opposite direction. And so the electrons would also experience a helical path, but if the protons are going this way, the electrons would be going that way, but with a tighter circle. But what if the particles are really moving? You know, like they're moving close to the speed of light. Really close to the speed of light. Then what will happen is that the radius of this circular path can be bigger than the radius of the Earth. And so the deflection then will just create kind of like a bow wave for a ship. And so the really most energetic particles will just be deflected in such a way, this will compress the magnetic field on this side and extend the magnetic field on this side. So the magnetic field extends out like that, it gets compressed because of the interaction of these charged particles. And so this looks almost like the bow wave of a ship. And on the rear side of it, that's like the wave when it's going away from the Earth. And so the most harmful particles then are completely avoid the Earth. And the ones that are lower in energy are deflected toward the poles. And so this is what creates the aurora effects, the northern and southern lights, is that these charged particles move in, they ionize the atmosphere, and they create some kind of spectacular, usually blue and green lights that are associated with ionization of nitrogen and oxygen in the atmosphere. Sometimes you'll get some red, but if you have one of these aurora effects happening, and you're right in the middle of it, you could be getting equivalent of 100 chest x-rays worth of radiation. So my friend I was talking to when I was in Chamonix, France, was telling me about his adventures driving in northern Norway and how he saw this incredible, spectacular light show, because that's where you'll tend to see it, is up near the poles, where these charged particles are deflected. He said, and it was just raining down on him, and I didn't have the heart to tell him that he got probably several hundred chest x-rays worth of radiation for that experience, but maybe it was worth it. Any questions about any of these applications? Yeah.
So there's lights in the south, right?
Yes.
Okay.
Yeah, that, I think it's called Aurora Borealis in the northern hemisphere, and Corona Australis or something in the southern hemisphere, but you get the same effect, yeah.
Does the sun let off one or the other particles more often than not, like more positive particles, more negative particles? And then, does that change the way the lights look?
You can certainly get more radiation from an electron, because the electrons have a tighter radius. So that means they're accelerating more, and when a charged particle accelerates more, it gives off more radiation. But they're not going to take the same trajectory along the radiation belts. They'll have their own little, they'll be going in the opposite direction. They could probably even slam into each other once in a while, because some would be going around this way, some would be going around that way, might even hit each other. And maybe that produces some other kinds of effects too. Question?
I was just wondering what would cause a similar effect in localized regions, like we had Northern Lights and slope a little bit. That's not very common.
That's a good question. The sun also has its own magnetic fields, and so here is a kind of a tangled web of magnetism that's produced on the solar surface. And so what this does is this tends to create magnetic storms. And so this kind of magnetism is not fully well understood, but we think that it has to do with the fact that the sun is moving differentially at the equator versus the poles. It's moving faster at the equator than it is at the poles. It's also spinning about 3 times faster in the core than it is out at the surface. So the effect of all of this is to create magnetism on the surface. And so if we look at it a little more simply, we would just have sunspots. So these are like magnetic storms. So in a sunspot pair, this is like the north and the south pole of a bar magnet. You have magnetic field lines that extend much like a horseshoe magnet was beneath the surface. Even though there's not really a horseshoe magnet on there, the field lines look as if there were. And so what will happen then is that charged particles will be evaporated from the sun, but will follow along in these closed loops. And that creates things like prominences, stuff like that. But every now and then, these sunspots are born bad. They have south poles leading a north pole. So then you have something called recombination, where you can have magnetic field lines. This one might be going like that, and this one might be going like that, and you get what's called recombination here. And when these things combine together, it creates a different magnetic field pattern. And it looks like the magnetic field lines are exploding. But in reality, what's happening is that they're just adjusting to a more stable configuration. And so what that tends to do then is cause what are called solar flares. So solar flares are these big explosions that usually happen in the vicinity of sunspots. And once that happens, the magnetic field in this region of space opens up. So it's no longer curved back on itself. So these particles then can spiral out, and this is what we call the solar wind. Okay, so the solar wind is controlled by these sunspot pairs, that when the sunspot pairs recombine, what you can get is a gigantic explosion, and the solar wind can go up by a factor of 1,000. And so you get enough of those particles, 1,000 times more, during a proton event like this, then they get to the Earth, and then it overloads the Earth's defense mechanisms. And that means that the magnetic field lines that are going to lower latitudes can also have charged particles moving along those paths, and so you can get the auroras farther south. So they tend to happen when you have more active sunspot conditions, because more magnetic storms means more possibility for recombination, means more explosions, and a greater amount of solar wind. Any other questions? Okay, so next, what I wanted to do is look at a cyclotron. Oh no, that's not. I wanted to finish off the mass spectrum. Do that next. Okay, so once we have this process of velocity selection and we understand what's happening with circular motion, what we can do is take those particles that have a known velocity and fire them into a region of uniform magnetic field. So here we've selected the velocity. This was plus, minus, this was E, and then B was into the board. So in this process then we have velocity is equal to E over B. And then we send those particles with a known velocity into a region of uniform magnetic field. So now we know what the velocity is, and when it goes into this region, let's say it's a positive ion. And this is an isotope source here. So this has a certain combination of heavy atoms that have more neutrons in them. Okay, and so a lot of times if you want to date something, what you do is you look at the relative concentrations of isotopes. For example, carbon-14 to carbon-12. That can give you an idea of how old the sample is, because you know what what's called the half-life of carbon-14 is. So the relative amount of carbon-14 that's in your sample then can, if you do a little bit of math, it can give you the data, the age of the sample. So once it comes in here, it's got a certain known velocity, QV cross B, so that's going to curve it up if it's a positive ion, and then it's going to hit up here. At a radius R, it's equal to mv over qv. And that's twice the radius where it's going to hit. Okay, so the radius is mv over qv, but twice that radius is going to be the location where this particular mass hits. And so where this mass would hit then, this would be R2, up to here. For R1, this would be 2m naught v over qv. Okay, so m naught might be your original mass, maybe carbon-12 instead of carbon-14. So that would hit more times here. And then the carbon-14 would hit more times here. So you could have a counter that counts how many times it hits, and then that gives you your relative concentration of carbon-14 to carbon-12 in your sample. Okay, so this is an interesting example in that, first we create ions, and then we accelerate them through an electric potential to get them going a certain typical velocity. We have an electric field in here that's accelerating them. Now they're traveling with a typical velocity, but then we want to screen off the ones that are a little off from that. And so we just let the particles go through that little slip. So if the velocity is a little too low, it goes down there. If the velocity is a little too high, it hits up here. And only the ones that have that known velocity go through. Because if we don't know what that velocity is, then that's going to mess up our mass, because there's two unknowns there. We don't know what the velocity or the mass is. And so this creates a situation then where the mass is known, and we can count the number of hits to determine the relative concentration of that isotope. Any questions about that? Okay, so I've asked questions before in exams quite a few times. Just outline the design of a mass spectrometer, show all the equations, draw clear label pictures. Next, I'd like to look at the design for cyclotron. Cyclotron is a particle accelerator. The first cyclotron was made at UC Berkeley. And the idea of the cyclotron is that you want to get particles going to a very high velocity, and then you can remove them from the cyclotron, and then they can be used in different kinds of experiments. For example, high energy particles at the Stanford Linear Accelerator are turned into X-rays by taking a magnet and accelerating the electron near the end of its path and producing X-rays. And those X-rays, because of conservation momentum, move in the same direction as the particles were moving. So if you have a well-defined beam of electrons, let's say, and then you accelerate them back and forth like this, that'll produce an X-ray that's pointed in that same direction. Then you can use that X-ray in diffraction to take a picture of something. And so you can image things. There's lots of really cool sorts of applications you can get for high energy particles. And so the cyclotron is a way of making it. Okay, and so the idea then is that you have some sort of a constant magnetic field. Let's make the magnetic field come out of the board. And then what you're going to want to do is accelerate charged particles through an accelerating potential here. So you move it through this accelerating potential, and then the particles move into a region that is kind of U-shaped like this, of constant magnetic field. So the particles now are moving. So we do Q, V. Make sure this way. So here's a positive charge. It's moving to the right. It's gotten a little bit of electric potential acceleration. So we do Q, V cross B. So that's going to cause a force that is going to make it go around in a circle like this. And then when it gets to this point, the electric field is reversed. Okay, so the electric field points to the left when it's up here, and then by the time it goes through half a cycle later, he is reversed. So we could have this whole thing set up and hooked up to an oscillator, an AC source that produces the electric field within this region. So that, because you don't want the electric field going the same way here, that would just slow the particle back down again. So you reverse the direction of the electric field when it gets to here and accelerates it a little more. So it's going to start out at some smaller radius, like this. And then it's going to be accelerated. It'll go to a slightly larger radius, accelerate it again, go to a larger radius, accelerate it again, go to a larger radius, accelerate it again, over and over again. And the electric field keeps changing each half cycle in order to keep it accelerating until finally it reaches the point where you run out of radius. And so at that point, you can have the particle, whether it's negative or positive, exit the accelerator. Then we could turn it into X-rays, or you might do some kind of electron diffraction. Electrons themselves have wave-like properties and can be used for diffraction themselves. And so the basic design then is to write this as QVB equals mv squared over r. And r is some variable radius, because the radius is going to be changing. And so you might be saying, well, then how do you know when to switch the electric field if the radius is changing? And you've got a lot of particles that might be at different points in their acceleration that are out of phase with this particle. How does that work? Well, if we rewrite this, we can cancel out one factor of v. We can get v over r equals qb over m. But does anybody remember what v over r is equal to?
Radial velocity.
Good. This is our angular velocity, omega. Okay, and omega is 2 pi times the frequency. So what you can see then is that the frequency is velocity and radius independent. It only depends on q, b, and m. So that means that no matter what part of this, it accelerates a little more here, that brings it up to a higher radius, because r is equal to mv over qb. And so as the velocity goes up, because it gets accelerated in this little u section, that brings the velocity up, which brings the radius up by just the same amount, so that the omega value stays the same. And so then, half a cycle later, you just flip the polarity on your electric field, and then it keeps it going and brings it up to a higher radius. Then you pick it again, brings it up to a higher radius. And so we could say then that the frequency of this is equal to QB over 2 pi m. And so that's what we call a cyclotron frequency. So this is, again, a way in which you're not doing any work on the charged particles, but you're keeping them confined.